Okay, so just a reminder about some of the administrative stuff. Unit 3 exam is this week, so it is due this coming Sunday at midnight. But again, like I mentioned for past exams, I strongly recommend planning to complete it significantly earlier than that. I would recommend no later than Thursday night to plan to have it completed. And that way, if anything does go wrong, you have a full business day to get anything sorted out, reach out to me, find other options, etc. Um, the material is sections 5, 6, and 5, 7, as well as chapters 6 through 8. The sample Unit 3 exam has been available for a while now, since before break. So you can take a look at that to get a better idea of exactly the type of material that'll be on the actual exam. And yeah, I think everything else should be pretty similar to the Unit 2 exam. The plan for today is to start in the chapter 9, mathematical models and geometry. Just a bit of a motley assortment of different topics, and particularly to cover 9.1 through 9.3, um, how to set up a problem solving strategy, solving a couple money applications, and some geometry material. And then on Thursday, kind of continuing with the geometry applications. And that'll wrap up the material for the course. Next week, or this coming week, however you want to say it, is final exam week. So, proper final exam week is really Tuesday. What would it be? Maybe like the 10th or something, Tuesday the 10th through Friday the 13th. Um, but I'm opening the final exam this coming Friday, so a few days from today, at 9 a.m. So that way you have the whole weekend. I know that folks, especially in remote courses, sometimes weekends work a little better for you. If you want to take the exam that weekend before finals week, you're welcome to, but you're also certainly welcome to wait until the kind of proper final exam week and take it during that week. So you can take it anytime uh, from Friday the 6th, this coming Friday at 9 a.m. through Friday the 13th at 11:59 p.m. And the same thing applies to the final exam. I would strongly caution against waiting till the last minute to take it. I would plan to take it no later than maybe say Wednesday afternoon or evening, and that gives you a full business day or two to work out anything that might be that might come up. Note that the due date is Friday for this finals week, because over the weekend I'll be getting all of my exams graded, everything turned around, and that way I'll be able to get grades posted in a timely fashion. You'll be able to get your grades quickly and so on. Um, so that is and the final exam is comprehensive, chapters 1 through 9. So everything we've covered in the course. And keep an eye out for the sample final exam to be posted in the next couple of days or so. I don't want to post it too early because I don't want it getting jumbled in with all of the Unit 3 exam stuff. But now that we've discussed the Unit 3 exam material, and there was the announcement before break, um, I'm a little more comfortable posting the final exam material now. So there will be a little bit of overlap between the Unit 3 exam time frame and the final exam time frame. It's just a little hectic because when we come back from Thanksgiving break, when Thanksgiving is this late, we really only have this 1 week, and then we're right into finals week. Any questions on any of the administrative stuff for the course? Okay. The quote of the day today is from my friend Mark. He works in finance in St. Louis. And he said this one time, and I thought it was just a really good aphorism. So I kept track of it. He said, 10 times out of 10, I take a questionable contract with a solid person over an ironclad contract with a questionable person. And this is something I've found to come up over and over again in life is, um, when you have the ability to deal with people who you would be comfortable taking a handshake agreement, and you don't need to have a contract written up. If you get to the point in if you get to the point in any kind of situation where you need to refer to the contract or go to court or something, it's everybody is already kind of lost, right? I mean, it's always good to have a contract so that just expectations are clear and all of that. But if you're having somebody, work on your house or work on your car, or if you're deciding which of a couple different job offers to accept or something like that, um, consider heavily the people that you'll be working with, not just the terms of the interactions. Um, I'd rather have a, a contract with less favorable terms to me, but have much lower counterparty risk uh, when it comes to dealing with the other person. And that being said, be the kind of person who somebody would be comfortable taking a handshake agreement from. That's always a good thing, right? You want to bring to the table what you're asking them to bring to the table as well. Okay, so moving into 9.1 using a problem-solving strategy. And the book outlines this problem-solving approach. So 7 steps. I think you almost need a strategy to remember and apply the strategy, but there are 7 steps. Read through the problem. So, this is almost self-explanatory, but sometimes we can jump the gun. So just take time to read through the problem, understand uh, what everything in the problem means, what the situation is, um, and then identify what we're looking for. Now, I would even go in somewhere in steps 1 and 2, and I would even add in uh, maybe a little side step. Can you bound the answer? Can I say, okay, I know that the answer should be a positive number? Can I say, okay, reasonability conditions suggest that the answer has to be less than 100, right? Can I figure out a bound on the answer? So to give me some way of kind of checking whether I'm on the right path, right? Can I figure out what units I want the answer to be in? So kind of setting myself up from the outset to be able to check my work as I go along or at the end. If I'm looking for, an answer in hours and I end up with an answer in miles, I've probably done something wrong somewhere. Okay, step 3, name what we're looking for. Choose a variable to represent that quantity. Step 4, translate into an equation. Um, perhaps restating maybe it's a full paragraph description, maybe restating it as a single sentence and then translating that sentence into mathematics, something like that, but translating into an algebraic equation of some sort. Solve the equation. So this is most of what we've focused on, step 5, um, so far in this course. Uh, check the answer and make sure it makes sense. So this is, this is referring back to this step here. Personally, I like to do this earlier, this step of like bounding the answer, getting the units. Number one, because I feel like, at least for me, I do a better job if I do it at the beginning. If I do it at the end, I feel like I've already answered the question. So it's just kind of like a formality almost. If I do it at the beginning, I'm looking forward and saying, what do I expect from the answer? I don't know the answer yet. And number two, that as I'm going through, sometimes I can check my answer as I go along, and I might even use, for instance, the knowledge of what units I want to end up with to help me formulate the equation in, say step 4, or to help me formulate what am I looking for in step 3. So personally, I like to do this a bit earlier. Um, and in my mind, make sure it makes sense is somewhat vague. Um, and then step 7, answer with a complete sentence. That's not that big of a deal. All right, so let's look at an example. We'll start with a fairly simple example. 1/4 of the candies in a bag are red. 1/4 of the candies in a bag are red. If there are 17 red candies, how many candies are in the bag? So I'm looking for the number of candies in the bag. And on one hand, I know that 1/4 of the candies are red. So the number of red candies is 1/4 of the total candies. And on the other hand, I know that the number of red candies is 17. So 1/4 of the candies in a bag is 17, or 1/4 of X is 17. I have gotten myself an algebraic equation, and I see I have 1/4 X equals 17. I want to, well, I've got my variable term isolated. I want to isolate my variable now. And I do that by multiplying by the reciprocal of the coefficient of X, or in other words, by multiplying both sides by 4. 4 times 1/4 times X is just 1 times X, or X. And X equals 17 times 4. We can come over here and do this multiplication. 4 times 7 is 28. 4 times 1 is 4 plus 2 is 6. And I have 68 candies. I guess one thing I can use to check if this makes sense is to say, well, of course, the total number of candies has to be bigger than the number of red candies. And it is. So 68 is bigger than 17, for instance. 1/4 of 68 is 17. I mean, I suppose we can check it that way. Basically checking our algebra, plugging in X equals 68 back in and making sure that both sides balance. But X equals 68 candy seems like a reasonable answer. Okay, let's look at a problem that's a little more abstract. The sum of two numbers is 0, and one number is 6 less than twice the other. Well, here I have two numbers. Let's call them X and Y. And their sum is 0. So on one hand, I have X plus Y equals 0 from this first sentence. And on the other hand, I have one number is 6 less than twice the other. So one number, let's say this one number we'll call X, is 6 less than twice the other. So twice Y, 6 less than that, 2Y minus 6. So again, my is kind of turns into an equal sign. One number X is 6 less than twice the other. It doesn't matter if you had chosen Y equals 2X minus 6. If you chose your X and Y that way, no problem. It's just a question of how we label things, or if you chose your numbers to be M and N or whatever. Now, I might look at this and say, well, what am I supposed to do with this? I have a linear equation in two variables over here, and I have another kind of a linear equation in two variables over here. I know how to solve one equation, one linear equation in one variable, but note that these two linear equations and two variables are actually kind of coupled. They both use X and Y. So in other words, like the X over here is the same as the X over here. But if X equals this stuff, anywhere that I see an X, I can choose to swap into Y minus 6, right? I could do that over here on the left. I could choose, instead of writing X here, I could choose to write 2Y minus 6. Since X equals 2Y minus 6, I'm going to write 2Y minus 6 in place of X. Plus Y equals 0. This plus Y and this equals 0 just kind of come down. And now what do I have? I have one linear equation and one variable Y. I have a left-hand side that can be simplified. Let me do that. 2Y plus Y is 3Y minus 6 equals 0. And now I have my equation in kind of standard form. Number times Y plus number on the left side and just a number on the right side. The first thing I want to do is if I have more than one variable term, I want to get them together, but I only have one variable term, y. The variable only comes up once in this equation, so I'm already good there. I then want to isolate my variable term. I have a 3y minus 6. My variable term has a minus 6 attached to it. I get rid of the minus 6 by adding 6 to both sides. 3y minus 6 plus 6 is 3y plus 0, or just 3y. And on the right, 0 plus 6 is 6. We might be able to solve this by inspection just by looking at it, but let's go through the last equation solving step. 3y equals 6. I want to isolate the variable. I multiply by the multiplicative inverse of the coefficient, 1/3. And I better multiply by that on both sides. So 1/3 times 3 times y is 1 times y, or just y. And 6 times 1/3 is 6 divided by 3, or 2. So I think one of my two numbers is y equals 2. And then I can plug back in up here into either of these equations to get x. Well, if x plus y equals 0, what number plus 2 has to be 0? That has to be -2. Does that check out with the other equation? If I plug in y equals 2 on the right side, I get 2 times 2 minus 6. That's 4 minus 6, or -2. That does check with the other equation as well. So I see that what I've just checked is using those two equations is first, that I have two numbers whose sum is 0. That's how I got the x in the first place. That is true. 2 plus -2 is 0. And second, that one number is 6 less than twice the other. X, or -2, is 6 less than twice 2. Twice 2 is 4. Subtract 6 gives me -2. And maybe I should say something like the two numbers are 2 and -2, or something like that. Any questions on this one? So one thing that makes word problems, maybe two things that make word problems challenging. One of them is there's just always another step, right? We don't have an equation given to us that we're working to solve. We have to somehow create the equation. So anytime that there's an extra step, that's going to make a problem more challenging than a problem where that extra step isn't involved. But also we have to translate these words into formulas. There are some key ideas that can help, like when I see the sum, that makes me think of addition. Is often translates to equals. The word of, there's the one I was looking for. The word of often translates to multiplication. So things like that, right? So there are some keywords that we can look for, and it's a little bit like a grammatical sentence, right? We kind of look for, I mean, we don't even realize we're doing it, but we kind of look for certain pieces to parse the grammar. We might look for the verb, and then before that is probably the subject, and after that is probably the object. So, sometimes if I can pluck out, okay, this is an equal sign, which I can't select it, but in this sense, maybe I see is, I think, okay, I think that might be an equal sign. Doesn't make sense that I'm equating two things. The sum of two numbers is 0. Sure, I'm equating two things here. The sum of two numbers and 0 are the same thing. And then once I get that equal sign, I can work with each of those two phrases independently. The sum of two numbers, okay, I need to figure out names for those two numbers. Let's just call them x and y. And then the other side of that is 0. Okay, and then one last example here. The sum of 3 consecutive integers is 39. Find the integers. So if I think of integers, I think of numbers like -2, -1, 0, 1, 2, 3, 4, 5, etc. if I pick three consecutive integers, it doesn't really matter which three. Maybe I'll go with these three. I note that consecutive integers are always 1 unit apart. So it's not just the sum of three integers is 39. There could be tons of solutions to that, right? Like 39 plus 1 and minus 1 or something, or 30 and 3 and 6, but the sum of three consecutive integers. So three that are in a row. Find the integers. I guess I could call the integers, the three consecutive integers, like x, y, and z, but that really kind of overcomplicates things. It wouldn't be the end of the world if I did that, but I'd have a lot of massaging to do before I got down to something like this, one equation and one unknown. But I noticed the pattern over here is I have a number and then one more and then one more still. Let me name the lowest of these integers x. So that'll be the smallest of the three integers. The next consecutive integer will be one more, x plus 1. And the next consecutive integer will be one more still, x plus 2. So my three consecutive integers, I'm not going to call them x, y, and z because they're so closely related. The relationship is easy enough to see at the beginning. I'm just going to say what they are in terms of, say, the lowest integer, the smallest integer x. But I see that the sum of these is, there's a keyword, that's probably going to be an equals. 39, that does make sense in this context to make that an equals. My first integer plus the second plus the third. The sum of the three consecutive integers is 39. So I've now gone through, I've understood the problem, I've converted everything into an algebraic equation after choosing a variable. Now I want to solve this algebraic equation. This is a linear equation in one variable. I know how to solve these. The right-hand side is as simple as it can get, just a number. The left-hand side, though, I can do some simplification. I see I have x plus x plus x, that's 3x. And then I have a plus 1 and plus 2 plus 3 equals 39. Okay, I might realize here that everything has a factor of 3 in it. I could divide, or I could multiply both sides by 1/3 to make things a little simpler off the bat. But no need to do that. We'll just follow our standard equation solving steps. If you saw that as a shortcut, you can certainly do that, but we don't need to. I have my equation in standard form, number times x plus number on the left, and just the number on the right. Nothing can be further simplified. I look across my equation and ask, do I see an x in more than one place? Is there more than one variable term in my equation? And no, there's not. I see that 3x, this is the only variable term. This is the only place that x shows up in the whole equation. So I don't have to combine my variable terms. That's already accomplished. But I do want to isolate my variable term, and I see I have a 3x plus 3. That plus 3 is attached on. I want to get that off with a minus 3. And as usual, I better do that to both sides. 3x plus 3 minus 3 is 3x plus 0, or just 3x. 39 minus 3 is 36. Now I have number times variable equals number. So I do one more equation solving step. I multiply by the multiplicative inverse of the coefficient. I multiply both sides by 1/3. 3 times 1/3 is 1. 1 times x is just x. 36 times 1/3, or that's 36 divided by 3. That ends up being 12. We might just know that 12 times 3 is 36. Or we can see that 3 is going to be a factor of 36 because 6 plus 3 is 9 and 3 is a factor of 9. We could do long division. We could take a few different approaches here. But we find that x equals 12. Looking back at our problem, we're not quite done yet. We were asked for 3 consecutive integers that sum to 39. So x is 12, but my 3 integers are 12, 13, and 14, right? 12, 12 plus 1, and 12 plus 2 are my 3 integers. And I can check, do these 3 integers, well, number 1, are they consecutive? Well, sure. And number 2, do they add to 39? Well, I have basically 10 plus 2, 10 plus 3, and 10 plus 4 all added together. The 10s add together to give me 30, 2, 3, and 4 to add together to give me 9. Yep, they do sum to 39. So that is my solution. Okay, any questions on section 9.1? Okay, so let's move into 9.2, solving money applications. And let's look at this first example. So Lee has $1.65 in dimes and nickels. The number of nickels is 15 more than the number of dimes. How many of each coin does he have? So let's say N is the number nickels and D is the number of dimes. We're looking for the number of each coin. We're looking for N and D. I know that in total, Lee has $1.65. If he had essentially all dimes, he'd have to have, at most, say 17 dimes. He couldn't have 17 or more dimes because then he'd have too much money. So D has to be less than 17 and bigger than or equal to 0. Maybe I'll write this as less than or equal to 16. Even though with 16 dimes, there's still a little bit of wiggle room at the top. There's not enough to add on a whole other dime. So basically, if he had as many dimes as he could possibly have, the most he could have is 16 dimes. That would be $1.60. Then he'd have to have 1 nickel to kind of round out the bit at the top. And of course, the least number of dimes he can have is 0. He can't have -5 dimes. What about nickels? Of course, nickels as well has to be bigger than or equal to 0. You can't have -10 nickels or something. Well, if he had 32 nickels, 32 times 5, 5 times 2 is 10, 5 times 3 is 6, plus 1 is, or I don't know where I got that from. 5 times 3 is 15, plus 1 is 16. So 32 nickels would give him $1.60. Right, 16 dimes would give $1.60. 32 nickels, 16 times 2, is the same amount of money in nickels. So he could have even one more nickel. He could have 165 cents worth of nickels if he had 33 nickels. So I've got some nice bounds on my answer. So what do I know? I know that, let's say, we could do this like $0.05 times the number of nickels plus $0.1 times the number of dimes equals $1.65. We could do it that way. That seems quite cumbersome, though. I have a lot of decimals and so on. I think I would rather think of all of this because dimes and nickels are easier to think about in terms of cents. And $1.65 is 165 cents. I'd rather think of it that way in terms of cents. So what units am I using? I'm going to use cents for units. So the total amount of money he has on one hand is 165 cents. And on the other hand is 5 times the number of nickels. That's how many cents he has in nickels. Plus 10 times the number of dimes. That's how many cents he has in dimes. So this is one equation that relates the number of nickels to the number of dimes. But I have another sentence. The number of nickels is 15 more than the number of dimes. The number of nickels is n, and that is 15 more than the number of dimes. That's d plus 15. That's a second independent equation relating n and d. And just like one of our previous examples, I know that I can replace n anywhere I see an n with d plus 15 because those two things are equal. Which means instead of writing an n here, I could write d plus 15 in place of that n. So I have 5 times, instead of 5 times n, 5 times d plus 15. Make sure that that's in parentheses because that n that's multiplying the 5 is being replaced by the whole thing, d plus 15, that's multiplying the 5. Now I look at this and I do have one linear equation in one variable, the number of dimes. I can figure out the number of dimes and then come back up here to one of these two equations, plug the number of dimes, d back in, and figure out the number of nickels from there. So I'm going to start off by finding d, the number of dimes. I can simplify this a little bit. I can use a distributive property here. 5 times d plus 5 times 15 plus 10d equals 165. 5d plus 10d is 15d. What's 15 times 5? That ends up being 75. So 15d plus 75 equals 165. I could have simplified this down, divided everything by 15. Again, if you saw that I have 15d plus 15 times 5 equals, and 165 actually is 15 times 11. So you might have happened to see that. You can divide everything by 15, make the numbers a little more manageable. But again, no need to do that. We can just follow our equation solving steps. So if you happen to see a little trick that you can use to make things easier, go ahead and use it. Just make sure you're using valid algebra. But if you don't see that, you can always just follow the basic equation solving steps. I look at my equation now and I ask, okay, well, I have a linear equation. It's in simplest form, number times variable plus number on both sides. On the right side, I basically have 0 times d plus 165. So that's in standard form. Do I need to combine variable terms together? Do I have more than one variable term? Nope, I only have 15d. I don't have d popping up anywhere else in the equation, so I don't need to do that step. My next step is to isolate the variable term to get that plus 75 off of the 15d term. To get that plus 75 off of there, I have to subtract 75, and I better do that to both sides. So I have 15d equals 165 minus 75. Well, 75 is like 65 plus 10. So this is like 165 minus 65 minus 10, right? 165 minus 65 is 100, minus another 10 is 90. So that's a quick way to do that subtraction. 15d equals 90. I've now isolated my variable term. My 15d is by itself. And now I want to isolate my variable. I want to multiply both sides by 1/15. 1/15 times 15 times d is 1 times d, or just d. 90 divided by 15, well, 15 times 2 is 30, and 30 times 3 is 90, so 2 times 3 is 6. Does it make sense that Lee could have 6 dimes? Yeah, that is a number between 0 and 16, so that passes the kind of reasonability check that we came up with before. If Lee has 6 dimes, how many nickels does he have? 15 more than the number of dimes. N equals D plus 15, or the number of dimes is 6, so 6 plus 15 is 21. And then we could check, is it true that 6 dimes plus 21 nickels is $1.65? Well, 21 nickels, 21 times 5 is like 20 times 5 plus 1 times 5, that's 105. Plus 6 dimes plus 60, 105 plus 60 is 165 cents, so that makes sense. And is it true that the number of nickels is 15 more than the number of dimes? Is it true that 21 is 15 more than 6? Yes, it is. So both of my criteria are satisfied, and this answer passes that reasonability condition up here, that the number of dimes and nickels fall between these numbers. Any questions on that problem? So at first glance, it seems like a big monster problem, but if you break it down kind of step by step, it's not too bad. Each of these two sentences, Lee has $1.65 in dimes and nickels. That translates to one equation. And the second sentence translates to a second equation. And we might get a little worried when we end up with two equations, but we just write them down and we ask, okay, is there any way I can simplify these down to just a single equation? And I do see that I can do that. And then the path forward is pretty straightforward. Once I get to this step, from this point, essentially all the way to the end, it's just a question of solving a linear equation, which we know how to do. Okay, so let's look at the next example here. So Mukul has 375 in quarters, dimes, and nickels in his pocket. We're going to throw in an Oxford comma because I like Oxford commas. He has 5 more dimes than quarters and 9 more nickels than quarters. How many of each coin are in his pocket? Here we have a pretty similar setup, but we have one more complication, that we have quarters, we have dimes, and we have nickels. Now his total money is $3.75. So just like before, obviously he has to have a non-negative number of quarters. He can't have -3/4. If he had all quarters, in no dimes and no nickels, forgetting about the other two criteria, what are the most quarters you could have and still be within this total? Well, 4 quarters makes $1. So 12 quarters makes $3 and 15 quarters makes $3.75. The most quarters that you could have is 15. How many dimes could he have? Well, 10 dimes makes $1, 30 dimes makes $3, 37 dimes makes $3.70. Any more he would go over. So he has to have less than or equal to 37 dimes. Can't draw a 3 apparently. 37 dimes. And of course, a non-negative number of dimes. And a nickel is half of a dime. So you could basically have twice that number of nickels. 37 times 2 is 74. And he could actually have one more nickel because he could squeeze in that last extra 5 cents for that 75. So he could have 37 times 2 or 74 plus one more nickel potentially. He could have up to 75 nickels total. So these are our kind of reasonability conditions. If I get an answer that says he has 17 quarters or that he has -2 dimes, I know that something has gone wrong somewhere. Okay. We're obviously looking for the number of each coin in his pocket. So we're looking for Q, D, and N. Somehow we have to use this criterion here as well as this one here. So the total number of cents in his pocket, I'm going to do this in cents again, is 375 cents. Each quarter is worth 25 cents. So 25Q. That's the number of cents coming from quarters. If he has 1 quarter in his pocket, he has 25 cents in quarters. If he has 3 quarters in his pocket, he has 75 cents in quarters, and so on. The number of cents coming from dimes is 10D. If he has 4 dimes in his pocket, he has 10 times 4 or 40 cents coming from dimes. And then the number of cents coming from nickels is 5N. The total number of cents coming from the nickels, dimes, and quarters has to be 375. That was the equation we got from our first sentence here, that the total is $3.75 or 375 cents. We have a couple more criteria though. He has 5 more dimes than quarters and 9 more nickels than quarters. This can be a little bit complicated to parse the sentence. We see and we almost want to add these together, right? It's almost like, do I take the first bit plus the second bit? But this and is really just acting as something like a grammatical conjunction. We have 2 more criteria, and we're putting them in the same sentence. I have one criterion, 5 more dimes than quarters, a second criterion, 9 more nickels than quarters. So this and in this case is not acting as like a mathematical operation. It's just acting as a conjunction that says we have this criterion and this other criterion as well that need to be satisfied. So he has 5 more dimes than quarters. That means that, well, the number of, so he has 5 more dimes than quarters. The number of dimes is quarters plus 5. Right? If we got confused, if we said, should it be like Q equals D plus 5 or D equals Q plus 5? Well, he has more dimes than quarters. So if he had like 1 quarter to have 5 more dimes than quarters, he'd have to have 6 dimes, right? So we could do a little trial and error like that, or think of which one has to be bigger. So because D, we have to have more dimes than quarters, D has to be the bigger one. We have to add the 5 onto Q to get D. So we have to increase the number of quarters by 5 to have the number of dimes. And similarly, he has 9 more nickels than quarters. The number of nickels is quarters plus 9. So this second sentence can be a little bit difficult to parse. I mean, the grammar itself is not super easy. And then turning this into mathematics does require some thought. And again, if you get a little confused which way it goes, try a number, right? Uh, okay, if I have 1 nickel and 10 quarters, do I have 9 more nickels than quarters? Well, no, that's the wrong way. If I had 10 nickels in 1 quarter, then I have 9 more nickels than quarters, right? So if I have 1 quarter and 10 nickels, that would be an example that would work out, that would satisfy this. So n has to be q plus 9, not the other way around. Now, again, I have, oh, let me use a different color. Again, I have d here, and I have d over here, but d is the same thing as q plus 5. I can swap a q plus 5 in. Similarly with n is the same thing as q plus 9. I can swap q plus 9 in over here. So I have 25q, that just comes down, plus 10 times, and instead of saying d, I'm going to say what d is equivalent to, q plus 5. Again, 10 multiplies like the entire d, so 10 needs to multiply the entire q plus 5. So we need parentheses around the q plus 5. We're going to have to distribute. And then plus 5n, that's 5 times the whole thing, q plus 9. And that's equal to 375. Now here I do notice that in each term I have a factor of 5. And I think I will at this point go and just make one simplification step. I'm going to divide both sides of the equation by 5. Again, you don't have to do this, but number one, this will make the numbers more manageable. And number two, I'm just going to show you as an example here. But you could proceed, you could look at this and say, okay, this is now one linear equation and one variable. I'll simplify the left-hand side and go through my equation solving steps. There's nothing wrong with that. But I noticed that if I have 1/5 times 25q plus 10 times q plus 5 plus 5 times q plus 9 and equals 1/5 times 375. On the left side, when I distribute this 1/5 to my 3 terms, 1/5 times 25, 25 over 5 is just 5. 1/5 times 10 times stuff is 10 over 5, or 2 times stuff. And 1/5 times 5, my q's and 9's are starting to look a little bit similar, but that's a q plus 9. 1/5 times 5 is just 1 times q plus 9. And on the right-hand side, 375 over 5, let's do that really quickly over here. 5 goes into 37. Well, 7 times 5 is 35. Leaving me with 2 left over. 5 goes into 25 5 times. So it looks like 375 divided by 5 is 75. So these are just a bit nicer numbers to deal with. Again, it didn't, it's not like I solved the equation in one step because I saw that trick. And it's not like if you didn't see that trick, you would be in for, 4 pages of algebra or something. But sometimes seeing a little trick like that can make things just a little bit easier. But if you don't see a trick like that, it's not a big deal just to proceed based off of that blue equation up there. But I have a similar structure now. I do see that I have one equation and one variable, the number of quarters. I want to simplify this left-hand side. So multiply out this middle term here. This 2 times q plus 5 turns into 2q plus 10. And 1 times q plus 9, those parentheses basically just go away. And my left side, I'll collect like terms. I have 5q plus 2q plus 1q. This q is like a 1q, right? So that is 8q plus 10 plus 9 is 19 equals 75. And now after all that work, I've gotten down to an equation in one variable, a linear equation in one variable, and I can solve this. It's in standard form. It's simplified on both sides. Do I have more than one variable term? Does the variable q pop up in more than one place? Nope, only in one place, just here with this 8q. I want to work to isolate the variable term. It has a plus 19 attached to that 8q term now, so let me subtract 19 from both sides. Or this is 8q equals. I might note that 19 is 20 minus 1. So 75 minus 19 is 75 minus 20 minus 1, or it's 75 minus 20 plus 1. So it's 55 plus 1, 56. Okay. If I get used to doing things like this, grouping things in, or kind of forcing things into the mode of where I'm adding or subtracting whole tens or whole hundreds or units this way, you can do arithmetic pretty quickly. So by making use of things like distributive property and so on, in interesting ways, you can do some of these more challenging arithmetic problems instead of having to go off to the side and do the whole subtraction method. You can do it maybe a little more quickly this way. But I have 8q equals 56. Now I have number times variable equals number. I've isolated the variable term successfully. I want to isolate the variable by multiplying by 1/8 on both sides. And q equals, what number times 8 is 56? That's 7. 7/4 is in the realm of reasonability. It's between 0 and 15, so that's good. I also need to know the number of dimes and nickels. I can get those from these two equations. The number of dimes is number of quarters plus 5. Or that 7 plus 5 is 12. So I have 12 dimes. And the number of nickels is number of quarters plus 9. Or that's 7 plus 9, or 16. Okay, any questions on this one? So even though this one has 3 variables in it, again, if we just kind of start from those first principles, we figure out what equations we're getting out of these sentences. Particularly the second one is a challenging sentence to parse and to figure out what it means. But once we break it apart, we see that there's really 2 criteria here, one there and one more. We write out those 2 criteria, and we see that we can end up with a linear equation, one variable that we can solve, then get our answer. And also 7, 12, and 16 all, so 12 is in that interval, 16 is in that interval, so they all satisfy this reasonability condition. Okay, and then one last example. Hilda has $306 worth of these 2 different types of stock shares, $10 and $12 stock shares. So a share of stock is just some proportional chunk of ownership in a company. So you can buy a share of Google stock or a share of Tesla stock or something like that. And there's two different types of stock shares here. Let's say that the $10 shares, we'll refer to those as X. X is the number of $10 shares. And the $12 shares, let's call those Y. Number of $12 shares. And we know the total value is $306. Or in particular, I know that each $10 share is worth $10, obviously. And I have X of those, so I have 10 times X is the number of dollars that I have invested in these $10 shares, plus 12Y is the number of dollars I have invested in the $12 shares, equals $306. Now I have a second criterion here in the second sentence. The number of $10 shares is 5 more than twice the number of $12 shares. I want to come up with an equation here, and I see this word is that kind of equating two things? The number of $10 shares it's the same number as 5 more than twice the number of $12 shares. Yeah, I think it is. So that is turns into an equal sign. The number of $10 shares, well, that is X. And what is X equal to? 5 more than twice the number of $12 shares, or 5 more than twice Y. Twice Y is, of course, 2Y. 5 more than that is 2Y plus 5. And just like before, I have this 10x plus 12y equals 306, and I have an equation in two variables, but I can use this constraint equation over here to get down to one variable. Instead of writing an x here, I can write what x is equivalent to 2y plus 5. And now I have 10 times 2y plus 5 plus 12y equals 306. Now I do have one linear equation in one variable. I know how to solve this. I simplify both sides, get down to number times variable plus number on both sides, and then I do my equation solving steps. So to simplify, I'm going to distribute first. 10 times 2 is 20y, plus 10 times 5 is 50, plus 12y equals 306. I can combine like terms. 20y plus 12y is 32y, plus 50 equals 306. Now I look at this and I say, okay, I have an equation, a linear equation in one variable that's in kind of simplest form or standard form, number times variable plus number on both sides. Do I have my variable term? Do I have more than one variable term? Do I have my variable in more than one place? No, I don't. My variable terms are, already combined in some sense or don't need to be combined. So now I want to isolate my variable term. I want to get this 32y by itself. It currently has a plus 50 added onto it. So I subtract 50 from the left side, and I'd better do that to the right side as well. 32y plus 50 minus 50 is just 32y. 306 minus 50 is 256. Right. What's my shortcut here? 306 minus 50. Well, this is like 300 plus 6 minus 50. And I know that 300 minus 50 is 250 plus 6, or 256. Now I have number times variable equals number. I've isolated the variable term successfully. And now I isolate the variable itself by dividing by the coefficient of the variable. Can either think of it as dividing by 32, or I can think of it as multiplying by the multiplicative inverse, 1 over 32. I usually say it as multiplying by the multiplicative inverse because, hypothetically, if we had come up with, 3/4 y equals 256, dividing by 3/4 is just a little bit annoying. It's easy to make a mistake there, but multiplying by 4/3, the multiplicative inverse, is a little bit less error prone. So just side note on why I tend to say it in a way that maybe seems a little more overcomplicated, but it's more general, I think. But 1/32 times 32 is 1 times y is just y equals 256 over 32. I might recognize that 256 is 128 times 2. And 32 is 16 times 2. And I can divide those out. I still have even numbers. I might even recognize that there's a factor of 4 in the top and bottom. 120 is like 30 times 4. And 8 more is like 2 times 4. So 32 times 4. I might also just recognize they're even numbers on top and bottom and keep chipping away using factors of 2, or I might do long division, right? Lots of ways to handle this. 16 is 4 times 4, and my 4's divide out. And 32 over 4, well, I know 4 times 8 is 32. So all of this to get down to y equals 8. So we are saying that we have 8 $12 shares. Maybe I'll say it this way, 8 of the $12 shares. And if y is 8, what is the number of $10 shares? What is x? It's 5 more than twice the number of $12 shares. Or that's 16 plus 5. That's 21. And we have 21 of the $10 shares. So we're looking to have around $300 worth of shares. 21 $10 shares is around $200. 8 $12 shares, that's like 90 something. That's around $100. 200 plus 100 is around 300. That seems like it's in the ballpark, right? Of course, I could plug back in and make sure that they work exactly, but this kind of passes the gut check. Seems about right. So passes kind of a reasonability test. Any questions on any of these problems in the first two sections here? Okay. Oh, I didn't add spaces in here apparently, or either I didn't add them in or they didn't take. Okay, section 9.3, use the properties of angles, triangles, and Pythagorean theorem to solve geometry problems. Let's look at the first example here. The measures of two angles of a triangle are 108 degrees and 36 degrees. Find the measure of the third angle in degrees. So a triangle, of course, is a geometric figure with three vertices, 3 points of intersection, and three edges connecting those three vertices. So we all know what a triangle is, but we might not know or might have forgotten that it's called a triangle because tri, like tricycle, the word for three, or the prefix for three, and angle, it has three angles. So it has three sides, but that means it has three angles. And if I call these angles maybe A, B, and C, a property of triangles is that A plus B plus C has to be 180 degrees. The three angles in a triangle always add up to 180 degrees. So whether your triangle looks like this one or, looks, there's all kinds of different ways a triangle can look like this, or, oh, one that's trying to be super helpful, or a triangle that looks like this, right? If I kind of take that top point and move it way off to the left, well, this angle gets a lot bigger, but these ones get smaller. I sometimes have a special case, a right triangle, where two of my sides are perpendicular to one another. They meet at a 90-degree angle. Usually with a right triangle, I'll draw that a little bigger. We indicate that it's a right triangle by drawing a little square in there. But even with a right triangle, the same thing applies. The sum of the three angles is 180 degrees. So if the measures of two of the angles are 108 degrees and 36 degrees, let's just call these A and B. Then what's the measure of the third angle, C? In other words, I have 108 degrees plus 36 degrees plus angle C equals 180 degrees. Degrees are just like units. It's just like inches or hours or something. If I have two things that have the same unit on it, I can add them together. So I can add together 108 degrees and 36 degrees, and I just get 108 plus 36 degrees at the end. So this is going to be 108 plus 30 plus 6, or 138 plus 6. That's 144 degrees. Plus angle C has to be 180 degrees. And here I can see that I have a pretty simple, but still a linear equation in one variable that's in standard form, or it's in a simplified form. I have only one variable term. The variable C only comes up in one place, so I don't need to combine variable terms. I do need to isolate my variable term. On my variable term, I have a plus 144 degrees, so I subtract 144 degrees from both sides. Just like addition, I can subtract things that are the same unit. And on the left side, I have just C, 144 degrees minus 144 degrees is 0. And on the right side, 180 minus 144, or in other words, what would I need to add to 144 to get 80? If I added 30, that would be almost enough. That would bring me up to 174, and I would need 6 more. So 36 degrees. So I can either set up an equation like this, or if I get more used to solving these problems, I might be able to just jump straight to maybe an equivalent equation that's like C equals 180 degrees. That's the total that I need. Some of that is taken up from the first angle, 180 degrees, 108 degrees. And some more of that is taken out from the second angle, 36 degrees. So I might just be able to jump straight to something like this and just do the final arithmetic when I get more used to these problems. But we always can just kind of follow the most straightforward strategy, end up with a linear equation and solve it. There's no problem there. And just as a little aside, we only had a coefficient of 1 on the variable, so we didn't have to do an additional equation solving step at the end. We just needed to subtract that 144 and we were done. We didn't need to divide by the coefficient because our coefficient was already 1. So what about this example? One angle of a right triangle measures 23.5 degrees. So a right triangle is one where one of the angles is 90 degrees. So we put that little square there, but that indicates an angle of 90 degrees. And it's saying one angle of a right triangle measures 23.5 degrees. Well, obviously that's not the 90-degree angle. Maybe that's this one, 23.5 degrees. What's the measure of the other angle in degrees? Maybe we'll call this one, say, B. So I know that B plus 23.5 degrees plus 90 degrees equals 180 degrees. This 180 comes from knowledge from geometry that a triangle has 180 degrees. So again, I have a linear equation here for B. This left side can be simplified a little bit. B plus 90 plus 20 is 110, plus 3.5 more is 113.5 degrees. So B plus 113.5 degrees equals 180 degrees. And now I have a linear equation in B. Both sides are simplified. I see that I have just one variable term. No need to combine variable terms. But that variable term is not isolated, so I'll subtract 113.5 degrees from both sides to isolate the variable term and get B equals, well, 180 minus 113.5. Let's just come off here to the side and do this. Sometimes it's just easier to do the subtraction. I think this might be one of those cases. So I can borrow, make a 7 and a 10. I can borrow again, make a 9 and a 10. 10 minus 5 is 5. Bring down the decimal point. 9 minus 3 is 6. 7 minus 1 is 6. 1 minus 1 is 0. And we get 66.5 degrees. Any questions so far? So one thing that we need for these types of problems is this piece of knowledge, right? This isn't something that we can get from the problem statement itself or something like that. It's a piece of knowledge about mathematics and geometry that we just need to know, that the sum of the angles in a triangle is 180 degrees. Okay, so what about similar triangles in this example? So here we're told that triangle ABC is similar to triangle XYZ. We want to find the length of side B. We want to find the length of this side down here. What a similar triangle means, when I say triangle ABC is similar to triangle XYZ, it means that the distance from A to B relative to the distance from X to Y, that proportion is the same as the proportion of the distance from B to C and from Y to Z. And that's the same proportion as the distance, say, from X to Z and from A to C. So ABC, we wrote that triangle with A on the bottom left, C on the bottom right, and B up top. And triangle XYZ, we wrote that with X on the bottom left, Z on the bottom right, and Y on top. So the triangles are written in a way that is consistent with how they're written up here. And we're told these two triangles are similar. Now I want to find the length of side B. It's in proportion to side 8. And it's in proportion with respect to, say, for instance, 15 to 10. Side B over 8 equals 15 over 10. I could say if I wanted to, that's also equal to 9 over x over little x, this side over here. But that's just not super helpful, right? We don't know anything about x. We're not looking to find x. So writing b over 8 equals 9 over x doesn't really help me to find b. But writing b over 8 equals 15 over 10, that is helpful. Or I can really think of this as like 1/8 b equals 15 over 10. And I see I can multiply both sides by 8. Well, 15 is 5 times 3. 10 is 5 times 2. So 15 tenths is 3 halves. 8 over 2 is 4. 4 times 3 is 12. So if these two triangles are similar, B must be 12. So similar triangles mean that their sides are in proportion to one another. Or another way to think about similar triangles is that the angles are the same. So angle C and angle Z, they have the same angle. Angle B and Y, same angle. Angle A and X, same angle. Okay, so moving on to the Pythagorean theorem. Let's look at this example. We want to use the Pythagorean theorem to find the length of the hypotenuse. Let's take just a minute here to discuss the Pythagorean theorem because it's, you know, kind of a big deal. It's probably one of the most, or probably the most known or recognizable, at least name of a theorem in math. So the Pythagorean theorem says the following: for a right triangle, this only applies to right triangles. It doesn't apply to general triangles, where we have, say, side lengths A and B and hypotenuse C. So how do I tell which ones are the sides and which one's the hypotenuse? The hypotenuse is opposite the 90-degree angle, and the sides are adjacent to the 90-degree angle. Note that if there's one 90-degree angle, there can't be another one. Let's say that I thought this was also a 90-degree angle. Well, then what can my third angle be? I mean, I have a total of 180 degrees in a triangle. If I've used 90 in one angle and 90 in another angle, I've already used up the whole 180 degrees. This angle would have to be 0. But if I have an angle that's 0, that's just like two lines laying on top of one another. That's not a triangle, right? So my other angles must be less than 90 degrees. As an aside, we call those acute angles. Acute angles are less than 90 degrees. Obtuse angles are bigger than 90 degrees. But if I have one right angle, the other angles must be strictly less than 90 degrees for both of them. So there's never going to be ambiguity where you say, well, which 90-degree angle am I talking about? Which one is the hypotenuse? If there's a 90-degree angle, it can be the only angle that's 90 degrees. And there's always going to be one side opposite it. That side length is C here, the hypotenuse. And the sides are the two sides the two edges that touch that 90-degree vertex, and those are side lengths A and B. The Pythagorean theorem says if we have a right triangle with sides A and B, hypotenuse C, then A squared plus B squared equals C squared. And there are like 1,000 proofs of the Pythagorean theorem. Let's look at one of them. It's a nice visual proof, I think. So let's consider, and make sure I draw this nicely here. So let's consider why isn't this dot undoing? There we go. Okay. Let's consider 4 triangles. I'm going to try to draw them so that they look roughly the same. All right. I think I need to give myself some points of reference here. There we go. So let's consider 4 triangles in the 4 corners of a square like this. And each of these 4 triangles, if I look at them, they are right triangles because they're in the corners of a square. And they have a hypotenuse that's opposite the right angle. We'll call that length C. So in the middle here, this blue square has area C squared. My running out of colors here, so maybe I'll just reuse black. My triangles are all going to be the same type of triangle. This short side I'm going to call A. And this longer side I'm going to call B. So I see that I have in the corners here four of these triangles that are side lengths A and B and hypotenuse C, just like the one up here. Now what I can do with these triangles, I would like another color, but I don't really have one. What I can do with these triangles is maybe make a copy of this. Move it over here. So first I can imagine sliding this triangle down here. Up this direction. Let me get rid of this C squared in the middle here. Let me also get rid of these C's. We don't need them at the moment. So I can imagine sliding this triangle kind of up and to the left. To make something like this, where I have side length B and side length A. That will free up the bottom right down here. So I end up with something like that. So what I did was slide this bottom right triangle up to kind of meet up with the top left triangle. Oh, there. Now what I can do is I can take these 2 triangles, the bottom left and top right triangle, and slide the bottom left all the way to the right, and slide the top right triangle all the way down. So if I do that, let me think copying this again is probably the way to go. So if I slide this top right triangle all the way down. Let me get rid of these C's. I don't need these anymore. If I slide this top right triangle all the way down, it comes down like this. This side length is B, and this one is now A. And I can get rid of this up there. I slid that down. And then I want to take this bottom left triangle and slide it to the right so that it meshes, that those hypotenuses kind of come together. So I can slide this bottom left triangle all the way to the right so that it meshes with that triangle that's now at the bottom right. And what I end up with is a square on the bottom left here. So maybe I'll highlight these. So the triangles up here, the areas of those four triangles are these pink areas. And then the leftover white area is what's C squared. Over here, I have these pink areas. In this intermediate step. And then down here, I have these pink areas. Just so we can kind of track what is what as we go along here. Now, I haven't made my overall square any bigger or smaller. I've just rearranged these pink areas on the inside. I know that the pink areas take up the same amount of space. I just move them around. That means the white area that's left over has to take up the same amount of space as well. I know on one hand, the white area takes up C squared amount of space. That's its area. On the other hand, I have now two little pieces of white area, two pieces of leftover area. Well, this top right area up here, this is just a square, right? Each of my sides overall is length A plus B. I just moved my A down here, so that puts a B up there. This is a square with side length B, or it has area B squared. And on the bottom left, likewise, if I have B over here now, this puts side length A here. This was always side length A. On the bottom left, I just have a quadrilateral with side lengths A everywhere. That's a square. With side length A, that has area A squared. So my total leftover white area on one hand is C squared, and on the other hand is A squared plus B squared when I combine together these two white areas over here. So this is, I think, probably the maybe most direct in some sense, visual and geometric proof of Pythagorean theorem. And this is how proofs, often proceeded, or maybe always proceeded, up until maybe, I don't know, 400 or 500 years ago or so. It was always about moving things around. Even when algebra started out and you had like quadratic equations or something, it was all about drawing pictures and moving things around. And it's a relatively recent development in math that we rely so heavily on algebra and almost leave geometry by the wayside altogether. But so this is a proof. I mean, some people would argue it's not quite formal enough, but it's a proof of Pythagorean theorem. So we know that if we have a right triangle with sides of lengths A and B and hypotenuse C, then A squared plus B squared equals C squared. Well, we want to find the length of the hypotenuse. We want to find the length of this missing side, C here. I note that we do have a right triangle. We're given side lengths A and B. we can use Pythagorean theorem to solve for c. So I have a squared plus b squared equals c squared, or I have 6 squared plus 8 squared equals c squared. 6 squared is 36. 8 squared is 64. 64 and 36 is 100. C squared is 100. What number multiplied by itself gives me 100? C must be 10. So the length of my hypotenuse has to be 10. As kind of a side note, I might notice that 6 is 2 times 3, 8 is 2 times 4, and 10 is 2 times 5. I actually have a similar triangle, so it would also be a right triangle, but have the same angles. That has side lengths 3 and 4 and hypotenuse 5. And this is a pretty famous triangle. The 3, 4, 5 triangle, the 3, 4, 5 Pythagorean triple. 3 squared plus 4 squared, 9 plus 16 equals 25, 5 squared. This is a good one to remember because if you remember this 3, 4, 5 triangle, that's a Pythagorean triple, a nice right triangle, a right triangle with integer numbers for the sides. You might recognize 6 and 8 as just 2 times 3 and 2 times 4, and then you can get the answer 2 times 5 right away using similar triangles without even having to do any work. Well, any of this arithmetic and all this down here. So we can actually use both of those ideas, either one of them, to solve this problem. Let's do it 2 different ways. I can use similar triangles. I notice that 15 is 5 times 3, that 9 is 3 times 3. My missing side must be 4 times 3. Right? So that I have my 3, 4, 5 triangle just scaled up by a factor of 3. It's a similar triangle. That 9 and 15, along with the fact that it's a right triangle down here, forces the issue. Now, something really important here is that the 15 is on the hypotenuse and the 9 is not. If I had a triangle like this, where I had 15 here and 9 here, that doesn't work. I mean, that doesn't work anyway, because the hypotenuse has to be the biggest one, but the point is, if I had something along these lines where I had the wrong similar number on the hypotenuse versus the side, then I can't use similar triangles to a 3, 4, 5, right? It is important that the 5 is the hypotenuse, so the analogous side on the similar triangle has to also be the hypotenuse and be related to 5. So I can find that the missing side has length 12. Let me box that since that's an answer, using similar triangles. I could also look at this and say, okay, well, if I call this side length b, I see that a squared plus b squared equals c squared, because this is a right triangle. So I'll call 9a, and 15 would be c, the hypotenuse. So 9 squared plus b squared equals 15 squared. 15 squared is 225. Is b squared plus 9 squared is 81. So then b squared is 225 minus 81. I did that a little bit fast. Sorry, I'm speeding up because we're running out of time, but let me be clear about all the steps that I'm doing. I have an equation for one of my variables. Now, this is a b squared that I have here. It's not a linear equation in b, but I can still kind of apply my same equation solving steps to isolate the b squared and then make an educated guess at what I think b ought to be. So I'm trying to get this b squared by itself. Right now I have b squared plus 81. I want to get the b squared by itself so I can do like I did up here. You know, if I get c squared equals 100, I can kind of guess, or through process of trial and error, I can say c's got to be 10. Trying to do a similar thing down here, get b squared by itself, b squared equals number, and then make a guess at what that number should be. So to do that, I'm isolating this variable term, the b squared term, by subtracting 81 from both sides. And 225 minus 81, 5 minus 1 is 4. And then we have like 22 minus 8 is 14. So b squared is 144. What is b then? Well, is it 10? Well, 10 squared is 100. So b is bigger than 10. 11 squared, we can multiply that out. That's 121. Still not quite big enough. What is 12 squared? Hey, 12 squared is exactly 144. So b is 12. I could solve it algebraically, and when I get to b squared equals 144, I kind of just use a bit of trial and error, unless I recognize 144 as 12 squared. Or I could use similar triangles. I think in this case, it's a lot easier to use similar triangles. Any questions on anything we talked about today? Okay, let me stop the recording.